Hello everyone, welcome back. In this video we're going to establish some more trigonometric identities and just talk in general about establishing trigonometric identities and then go on and establish some trigonometric identities. So in some previous videos we talked about some basic ones that come from geometry. One that we didn't mention yet was the one from the Pythagorean theorem, which the identity, I'll just state that first, is that cosine squared plus sine squared is 1, no matter what theta is. And why is that? Well, that's because x squared plus y squared equals 1 is the equation of the unit circle centered at the origin, and this comes from the Pythagorean theorem, which is that if you take x squared plus y squared, that gives you the distance from the origin squared. And so if it's 1, that means it's tracing out a unit circle. Okay. Also, just to make this Pythagorean theorem look more, like where you can see the triangle. If you have a triangle of base cosine theta and of height sine theta, then its hypotenuse is 1. And this works for all quadrants, even for when, quadrants 2, 3, and 4, the triangle looks funky with negative side lengths, but it's still, the Pythagorean theorem still works. Okay, so what are we going to do? We're going to start just establishing some identities and see what we can do. So one thing to know about this is that there's not one way to establish an identity. All you need to do is show that the left-hand side is equal to the right-hand side. So one way to do it is you start with the left-hand side and you just keep manipulating it until you get the right-hand side. Or you start with the right-hand side and manipulate it until you get the left-hand side. Or there are many other things you can do as well. So what I'm going to do, let's just try going from the left-hand side. I'll start with 1 plus tan squared theta, and I know that tangent is sine of theta over cosine theta. I find that it can be a lot easier to take everything and just put it in terms of sine and cosine. Okay, so let's do this as 1 plus sine squared theta over cosine squared theta. And let's put it all together. So common denominator is cosine squared. Let's actually put it together. And then cosine squared plus sine squared, that just happens to be something that we know what it is. It's 1. And let's apply it. And this is, okay, so now here's the point where I know that I want to get secant squared. And secant is 1 over cosine. So let's look ahead, do it like that, and that is secant squared theta. Okay, so the left-hand side, LHS, equals the right-hand side. So we have established it. So you should think about establishing identities as sort of like wandering through a maze. There is a way to get from the beginning to the end. It's a problem that they've set for you, but it's very likely you'll hit dead ends along the way, but that's fine. You explore, and then once you manage to get from the beginning to the end, you're there. I'll mention also this particular identity. You can also get it from taking the original Pythagorean theorem identity, dividing both sides by cosine squared and simplifying it all. And then you get this. But I wanted to show you some of this algebra. Let's establish another identity. So we've got cosecant of theta times cosine of theta is equal to cotangent of theta. So let's recall cosecant of theta is 1 over sine of theta, and cotangent of theta is cosine theta over sine theta. So let's plug these in. So cosecant is 1 over sine, and cotangent is cosine theta over sine theta. And, you know, both sides are the same. So it's established. Yeah, so sometimes you get these weird combinations of functions, but it turns out to be something you already know if you were to just see how it was in terms of sines and cosines. Let's look at the next identity. Okay, this one is cosine cubed is cosine minus sine squared cosine. Just so you know, whenever you don't have parentheses like this, the assumption is that it's like so, and these are multiplied together. I just want to make sure you don't think it's that. Cosine is not being given as an argument. It's that these two functions are being multiplied. Okay, when you have something like this, what tends to work is whenever you have a power that is large, you can try to use the Pythagorean theorem identity. So here's what I mean. So let's write the identity here. If I subtract sine squared from both sides, I get that cosine squared is equal to 1 minus sine squared. So cosine cubed is cosine of x, cosine squared x. And yeah, so then cosine x can be multiplied by 1 minus sine squared x. And I can distribute cosine x minus sine squared x. And then let's use the commutative property of multiplication and write it like that. Yeah, okay, so it's been established. We've shown that the left-hand side equals the right-hand side. Let's just give that a check. Yeah, so I guess I was just sort of lucky that that was it. I probably could have also taken sine squared and replaced it with 1 minus cosine squared by subtracting cosine from both sides. And that's a good way also. Let's do that. Let's take cosine x minus sine squared x cosine x. And that is cosine x minus 1 minus cosine squared cosine x. Okay, so figure out why that's something I can do. And then this is cosine x minus, let's distribute cosine x minus cosine cubed x, which is cosine x minus cosine x plus cosine cubed x. The cosines cancel out and we're left with cosine cubed x, which is exactly the left-hand side. Okay, so that's that identity in two different ways. Let's go into our third one. So we want to establish that 1 over 1 minus sine of theta plus 1 over 1 plus sine of theta is 2 secant squared theta. Whenever you have some fractions like this, it's usually good to try to put them together, find some common denominator. So, and that's the complicated side. Usually if you start with the complicated side, you can find some simplifications and turn it into the less complicated side. So this is 1 over 1 minus sine theta times 1 plus sine theta over 1 plus sine theta plus 1 over 1 minus sine theta times 1 plus sine plus 1 minus sine theta over 1 minus sine theta. So then that gives me a common denominator of this whole quantity down there. And I have 1 plus sine theta plus 1 minus sine theta on top with 1 minus sine theta, 1 plus sine theta in the denominator. So here's a fact that is good to remember. Fact: if you have 1 minus x times 1 plus x, this is 1 minus x squared. So let's apply that with x as sine. So in the numerator, we've got 2, and the signs cancel out. In the denominator, we have 1 minus sine squared theta. Let's make a little space here. So 1 minus sine squared is cosine squared. Let's pull the 2 out and write it like this. This is 2 secant squared theta. That is exactly what we wanted to get. So we've established that this identity is true by going through these algebraic rules. For this final identity, we're just going to use it to remind ourselves about some logarithm rules. So this is the natural logarithm of the absolute value of secant of theta is equal to negative natural logarithm of cosine of theta. So for this one, I'm going to use my rule that can be good to switch over to using, just go to sine and cosine. So here, you need to know an absolute value rule, which is, so first of all, if you got a over b, absolute value, this is the absolute value of a over absolute value of b. If you have minus 2 over 5, that's the same as, and you do the absolute value, you can take the absolute value of minus 2 first and do 2 over 5. So I'm going to apply that here. And then absolute value of 1 is 1. And then let's write this as ln of cosine theta to the minus 1, because then we can use the logarithm rule that this is minus 1 times the natural logarithm of absolute value of cosine, and that's negative ln absolute value of cosine. Okay, so we've established these identities, and lots of identities are just using these similar principles. Just wander into the maze and hope you eventually find the end. You will. Just if you need to have a little bit of perseverance sometimes, but you'll ultimately get there. Okay, so that's it for this video, and I'll see you next time. Bye.